for the midterm exam. Okay, so we are starting a new section, and this section is on the digestive system. And so when we talk about the digestive system, we also talk about what is referred to as the alimentary canal. And so I never knew what that word meant, and I looked it up, and it means nutrition. So this is the alimentary canal. So that is from the mouth to the anus, right? Sometimes they call that the gastrointestinal tract or the GI tract, but that is actually from the stomach to the anus. So the entire tract is called the alimentary tract or alimentary canal. And then we also have accessory organs. So what's an example of an accessory organ to digestion? It's not part of the tract itself.
Gallbladder?
Gallbladder, which also connects to the liver, right? So the liver produces bile, and it releases that bile, or it's stored in the gallbladder, and then it gets released into the small intestine called the duodenum, the part of the small intestine called the duodenum. And then that helps to break down lipids. So that's a good example of an accessory organ. So when we look at the digestive tract, because we have food traveling in one direction, different things happen in different parts of the alimentary canal. So we say that the alimentary canal is compartmentalized. So there's a different chemical environment and different things are being broken down in the stomach compared to what is happening in the small intestine, for example. And so these are kind of the stages of the digestion. So we ingest it, we break it down, then it goes through the digestive tract. So we have propulsion, so we have to keep things moving. If stuff stops moving in the digestive tract, that can be a real sign of a big problem. So you want this movement, this propulsion, this peristalsis to continue. And they worry about that in the hospital if your digestive tract stops. And so one way that they try to get it to kind of reboot itself is by making you get out of bed and walk around. Okay? And so then obviously we also have the absorption of nutrients and the production of feces. So we're going to start in the oral cavity. And when we talk about the oral cavity, remember that it's separate from the nasal cavity by the hard palate, actually the hard and the soft palate. And so we have, in the oral cavity, we have different things going on. And we have, associated with this, the salivary glands. So we have some salivary glands that are located under your lower jaw, and these are called the submandibular glands. So underneath, and sometimes you can feel them. So you can put your thumb underneath the ridge of your lower jaw, and there's lymph nodes underneath there, but there's also salivary glands. So sometimes the salivary glands become swollen and tender to the touch as well. We also have a large salivary gland, which is called the parotid glands. And so these are located up here next to your masseter muscle on the side of your face. And these are actually what get infected during when people have an infection with the mumps virus. So this is the mumps virus. Causes this to particularly swell, right? And so that gives them kind of a chipmunk look to them. When we look at the salivary glands, we see that there are inside the salivary glands, obviously we have water, which functions to moisten the food. And it also aids in chemical breakdown of the food. So we also have some enzymes. We'll talk about one in a second. And then we also have IgA antibodies. And so those protect against infection. So if we look at an example of enzymatic digestion that takes place in the mouth, we have an enzyme that breaks down starch, which is a polysaccharide of glucose, into maltose. And this enzyme is called salivary amylase. So anytime we see that ACE ending, that means that it is an enzyme, although there are some enzymes that don't have that ACE ending. But if you see that ACE ending, it definitely means it's an enzyme. And so starch is not very sweet. And so you may have experienced eating starch. If, for example, you've ever taken a bite of a raw potato, that's kind of what starch tastes like before it's cooked and broken down. And so when we take starch into our mouth, it's broken down. And so the starch will actually be converted into maltose, and we'll be able to taste sweet on the surface of the tongue if it's left there for long enough. So chemical digestion does start in the oral cavity. So this would be an example of chemical digestion. Okay, so if we look at a diagram, you need to be able to identify the submandibular, and there's another group I forgot to mention. This is the sublingual. So this is, if you've ever had, or kids, sometimes they do this, right? They call it gleeking, right? And so they shoot saliva out through these glands. And so these have ducts underneath the tongue. I was never able to do that, but I, consciously caused them to constrict and shoot out saliva. So remember that these glands are examples of exocrine glands because they have ducts, and they're not endocrine glands which produce hormones. So they're exocrine glands that have ducts and deliver their substance to the inside of the mouth. And so notice that the parotid gland up here also has a parotid duct, right? And that actually enters in through the top of the mouth, which is interesting. So we get saliva there. And that's the biggest salivary gland. We can also see that we have in the oral cavity the tongue. And so the tongue is really interesting because it is skeletal muscle. But it has different types of skeletal muscle tissue in it. And so the skeletal muscle is broken down into intrinsic, where it is not attached, its movement is not due to the attachment to a bone or to a bony structure. And so it means that its attachment and its origin are inside the muscle itself. And so this is not attached to the bone, and it allows the tongue to change shape. So like if you were going to flatten out your tongue or make it big and wide and thick, that would be intrinsic muscle. Okay, so this is different than extrinsic muscle of the tongue. So this is where we have attachment to the bone. And we're going to watch a short video that is going to show what bones it is attached to. So it has an origin and an insertion point. And it allows the tongue to move like out to the outside, to be drawn back in, to move side to side. And so this is the actual movement of the tongue. Oops, tongue forward and backwards, side to side. So I'm going to show you a little video that talks about the tongue, and it also shows the tongue as it is in a cadaver. And so they did a cross section, or actually longitudinal section of the cadaver to show the structure of the tongue. Let's move this over here.
Bone and the muscles that hold it in place and move it. We'll move on to look at the tongue. The shape of the mobile anterior part of the tongue is familiar to us from everyday encounters. What's perhaps surprising is how much of the tongue we don't see from in front. The tongue goes a long way back and a long way down. To understand the overall shape of the tongue, let's look at a specimen that's been divided in the midline. All this is the tongue, right back to here. The tongue consists almost entirely of muscle, covered by a specialized mucous membrane. The freely mobile anterior part of the tongue almost fills the oral cavity. The massive posterior part of the tongue, which is much less mobile, faces backwards into the oral pharynx. This structure below and behind the back of the tongue is the epiglottis. We'll see it in the next section. To get a look at the intact tongue, we'll look at a specimen consisting of just the tongue, the mandible, and the hyoid bone. Here's the hyoid muscle. The body of the hyoid bone is here. Here's the greater horn. We'll look at the outside of the tongue first. The tongue is covered with mucous membrane on top, on the sides, and also here in front, on the underside. The mucous membrane of the tongue is continuous with the mucous membrane that covers the floor of the mouth and the alveolar process. There's a deep valley between the alveolar process and the side of the tongue. This projecting fold in the midline is the frenum. On either side of it, the submandibular ducts open, as we'll see later. The mucous membrane over the root of the tongue is thin and mobile. Over the sides of the upper surface, the mucous membrane is thick, firmly attached to the underlying muscle, and covered by projections called papillae. The largest of these, the valleculate papillae, are in a row back here. This shallow pit in the midline is the foramen cecum.
So the bones that he mentioned were specifically the hyoid bone. So the hyoid bone is back. So we can stop this.
The muscle.
So one of the
The
bones
muscles that form the bulk of the tongue.
One of the bones that the muscle, that the tongue muscle attaches to, that you can't see on here, is the hyoid bone. So remember that the hyoid bone is one of those bones that doesn't articulate with any other bone in your body. So it kind of just sits suspended here, and it actually connects to the styloid process. So there's a ligament, or a ligament that comes down and connects to the hyoid bone. And so the hyoid bone has or serves as an attachment point for the tongue muscle, as does the mandible. So the extrinsic tongue muscles attach to both of those, the hyoid bone and the mandible. So if we look at the function of the tongue, one function is it moves the food around. And so one thing that it does is it presses or moves the food so that it goes underneath the teeth, specifically the molar teeth, so that it can be ground up, the food can be ground up more completely. Right? It also has chemoreceptors on its surface. And these are taste buds. And so taste is a very unrefined sensation. We talked about this when we were looking at the sensory system, in that there's really only 4 or 5 different tastes. So there's sweet, sour, bitter, salty, and then umami, right? So we talked about those, didn't we? Mm-hmm. Yeah. Okay, so the taste buds give us some idea about the nutritional content of the food. And so we can crave, for example, salty food if we are lacking in salt in our diet. Okay. We also have the formation of a bolus. Oops, formation of a food bolus. And so a food bolus is a ball of food that we swallow, And we need to swallow our food in big pieces like that in order for the epiglottis to do its function and fold down so that the food doesn't go into our respiratory tract. So when people say don't inhale your food, that means we don't want to just breathe in, right? And breathe in and get little pieces of food, because those little pieces of food are going to be easily able to go into the trachea, and they're not going to push down on the epiglottis. So this bolus is important because it pushes down on the epiglottis and it closes off the trachea. Okay. So if we look at the surface of the tongue, there's actually a line of connective tissue that runs down the middle of it that creates a ridge, or not, excuse me, a little groove, a shallow groove. And so that's the sulcus. And then we can see the taste buds, which would contain chemoreceptors. And there's different types of taste buds. There's some on the back there. We also see way back on the tongue, the linguinal tonsil. And so remember that that is immune function, like the palatine tonsil and the pharyngeal tonsil. So when we talk about chemical digestion mechanical digestion in the mouth, we can talk about dentition. So this is mechanical digestion. So to chew your food is called what? Does anybody know the technical term of chewing your food? Yes, mastication. Okay. So that type of mechanical digestion increases the surface area over which enzymes can work. So it's important to chew your food, right, in order to fully break it down nutritionally. Sometimes if we don't chew our food properly, it actually comes out the other end, right? And it's actually in a solid form. So if you think of, like, people have said to me, peanuts or corn, right, sometimes comes out, like, and you see it in your feces. Like, yes, they didn't chew, yeah. So sometimes stuff does not get broken down completely, and that's because they didn't chew the food, they swallowed it, and then it wasn't able to be digested, and the nutrients weren't able to absorb. So that's why they say to chew your food well in order to get the most amount of nutrients out of it, okay? So when we look at the dentition, when we look at the tooth structure, the outermost part of the tooth is enamel. And they say that this is the strongest substance in the body. And that is primarily because it is a calcium phosphate mineral. So this is the mineral, it's mineral, calcium phosphate. It's very strong, but it is brittle. And this is the outer covering of the tooth. So sometimes that enamel can break off or become worn off, or sometimes bacteria can produce acid. And when we get these acid-producing bacteria in our mouth, it can lead to cavities because they break down the enamel and then they get inside the tissue and they just start feeding upon the tissue. So underneath the enamel, we have a bone-like substance, which is called dentin. So this is a bone-like substance. So does anybody remember what protein is found in bone that gives its strength? What protein? Collagen, right? So this has collagen fibers. So it's bone-like. Enamel does not have it. Enamel is inorganic. It's a mineral. It's just the minerals. Okay. And then we have the pulp. So the pulp consists of connective tissue with blood vessels and nerves. So this allows us to have sensation of feeling in our teeth. And we kind of ignore that sensation, but if you can just take a moment and just like see if you can really feel your teeth, right? So there's actually quite a bit of what we can feel in our teeth. So we could feel, for example, temperature. We could also feel pressure. Okay, so there's actually quite a bit of sensory information coming into us, into our nervous system from the teeth, okay? So this is where we have the root, right? So sometimes the root canal, the tooth can go bad and the root canal can become exposed or damaged, and then you have lots of pain. And so when they drill out the root, they get rid of the nervous tissue so that you don't feel it anymore. So it actually deadens the tooth and you wouldn't have any sensation in it. So if we look at the structure of the teeth, of the tooth, okay, so this is the outer enamel. This is the dentin. This is the pulp down in the center. And then we actually have the tooth sitting in to an indentation in the bone, so in the maxilla and the mandible. And so we actually have a set of ligaments that hold the tooth into the bone. And these are what are referred to as the periodontal ligaments. So these connect the tooth to the jawbone. And so sometimes you can get infection in the gum that kind of goes down into this periodontal region around the tooth. And so you can get like inflammation of the gums. So has anybody ever had like inflammation of the gums and the doctor was super concerned and actually put you on antibiotics because of it? So as you get older, anytime they actually measure your gums, anytime you go to the dentist to see if they're inflamed, so they actually get a measurement. And even if you have like a slightest bit of inflammation, they kind of freak out. And why is that? No, I'm talking to maybe not all the gums, but if like there's one part of the gum that's actually inflamed and swollen, then as you're older, the dentist becomes really super paranoid about that. And why? It's nothing about losing your teeth.
I know it's like the heart. Is it like constant? I know.
Yes, heart, right? Yeah. So periodontal disease starts with the gums, right? And this is where the bacteria get into the circulatory system. Right? And they actually cause inflammation and infection in the blood vessels, which can lead to atherosclerosis. So it can lead to the blood vessels getting, having plaque build up in them. And so it causes circulatory system diseases. It can lead to heart attacks, right? So you'll probably discover this when you go to the dentist when you get older, is this that it will immediately put you on antibiotics. And you're like, well, it's just a little bit inflamed. What's the big deal, right? And then they'll make you come back and make you come back and make you come back, right? And then finally it goes away and they're like, okay, now you can be, rest easy. Right? So they make a huge deal out of it. Okay. So if we look at our teeth, we actually have two sets of teeth. So we're born with what are sometimes referred to as deciduous teeth. Why do you think they're called deciduous? They fall off, right? So deciduous trees are the trees that lose their leaves in the winter. So deciduous means to fall away or to fall out. And then they're replaced by the adult teeth. And we have different types of adult teeth. So for example, we have incisors, which are in the front. And these are used for cutting, right? So if you're thinking about if you're eating a carrot and you need to clip it, right? Or a piece of celery, it cuts, right? You can also look and see that we have canines, and this is used for ripping. So if you have a piece of beef jerky, you're not going to use your front teeth to rip through it, right? It's going to hurt them. So you would put the beef jerky in the side and you would use the canines to tear, right? And then we have the premolars and the molars. The premolars are smaller. The molars, these are used for crushing and grinding. Okay, so the tongue works at pushing stuff underneath the teeth so that they can be ground more finely, the food can be ground more finely, and then the tongue takes that ground up food, creates a food bolus, and then you swallow it. So if we look at our digestive system, you'll notice that here we have the esophagus. Notice that you can tell the difference because there are no rings of hyaline cartilage. So the trachea has rings of hyaline cartilage, but notice how long the esophagus is. And notice that it's kind of running right down the midline of the body. So it is actually going to go behind the heart, through the thoracic cavity, and then it's actually got to pierce the diaphragm. So there's an opening that allows the esophagus to come through, and then the stomach and all the other digestive organs are in the abdominal cavity. Okay? So if we look at the esophagus, actually let's first talk about the histology first. So we're going to talk about the basic histology, and then we'll talk about the differences that we see in the different parts of the compartments of the alimentary canal. So there are 3 layers. So if we took a cross section, we have the innermost layer, and then a middle layer, and then the outermost layers. Eraser got involved here. Okay. So the space in the middle of the alimentary canal is called your lumen. Anytime you have a space, like the blood vessels have a lumen in them too, the digestive tract has a lumen. So the first layer is the mucosa. And this is a thin layer, and it is composed of epithelial tissue. Right? And it is the innermost layer. The next part of the layer is called actually there's 4 layers, sorry, 4 layers. It is called the submucosa. And so it is underneath the mucosa. So if the mucosa lines the lumen, and right underneath we have the submucosa. And in the submucosa we have connective tissue, and we have circulatory vessels and lymphatic tissue and nerve fibers. So mucosa. So this is connective tissue. Blood vessels, so blood and lymphatic vessels. And we have nerves. The next layer is the muscularis, and we're going to call it externae. So what type of muscle is found in the digestive system? Is it skeletal, smooth, or cardiac? Smooth muscle. So the contraction of the smooth muscle causes movement of the food, and it has a special name, and this is called peristalsis. So these are waves of contraction that force the food through the canal. Peristalsis. We also have the outer layer, which is referred to as the serosa, and it is connective tissue. Oops, serosa. This is connective tissue that lines the outside of the organ. This is also referred to as the visceral peritoneum.
It lines what?
It is the outer surface of the organs, like the outside of the stomach. So it lines the outside of the stomach, and it is called the visceral peritoneum. So when we do our dissection of the fetal pig, not this week, but next week, you'll be able to see that there's connective tissue surrounding all the organs, and then there's also connective tissue lining the body cavity. And so the body cavity in the abdominal cavity is actually called the peritoneum. So when we talk about, or the peritoneal cavity, peritoneal cavity. Okay. So this is in the abdominal region. This is not a layer. Abdominal region. Okay. And so this cavity is filled with fluid. So our organs are actually sitting in a fluid-filled cavity. And this allows the organs to move friction-free, but it also kind of cushions the organs. So sometimes you get illnesses that cause holes and like perhaps a burst or ruptured appendix. And you can get bacterial infections in your peritoneal cavity. And then they actually have to drain it and flush it out, and then give you lots of antibiotics to take care of an infection in this cavity. So this is a fluid-filled cavity where most of the digestive organs sit. So that's your peritoneal. As opposed to like the pleural cavity or the pericardial cavity, right? The peritoneal cavity. Okay, so if we look at a diagram of this, this shows the cavity. So this is a cross-section through the abdominal region, and it is lined by a serous membrane that produces fluid. And then you can also see that we have what are called mesenteries that connect and anchor the organs in your abdominal cavity. So they're not like just floating around in this fluid-filled space. They're actually anchored by mesenteries. So we want to write that down too, that organs are anchored via mesenteries. So this shows the peritoneal cavity. This shows the visceral peritoneum. And then the parietal peritoneum is what lines the body cavity. Okay. Fluid-filled space. Looking at a cross-section. Okay. So what you need to know here is the mucosa. So that's that innermost lining. It generally is just a single layer of cells, epithelial cells. So it could be columnar, simple columnar epithelial. This would be the submucosa. Oh, actually, let's use this as the submucosa. So notice that there's lymphatic vessels, there's nerves, there's also glands. And then this would be the external. So that's the muscularis externus. And notice how there's two layers. So we have longitudinal muscle layer and circular, and then the very outer is connective tissue. Okay. So let's talk about the esophagus first. Because food is traveling down through it, we need to have some protection against friction. And so this is stratified. So its mucosal layer would be stratified. squamous epithelial tissue. And you probably have felt food move down through your esophagus. Perhaps you swallowed a chip without completely chewing it, right? And it goes down and you can feel it scraping against the esophagus, right? So we do have friction. Sometimes you can also feel pills get stuck in your esophagus. And what happens there is they get stuck in the mucus, like say a vitamin, and it gets stuck there, and your esophagus keeps contracting, and it's really annoying because you can feel your esophagus keeping contracting to try to get it down, but there's really nothing you can do because it's stuck, right? And so when we look at the esophagus, this is involuntary muscular contraction. So as soon as we've swallowed, the pharynx, which is voluntary, once it gets to the esophagus, the contractions are involuntary. And it has to do with circular and longitudinal muscles. So I'm going to draw my esophagus here. The muscles that are circular are going around it like this. And so if a circular muscle contracts, it's going to force the esophagus to get thinner. So this would be the circular muscle. Okay. So what's going to happen is your esophagus is then going to get thin right in that particular area, like this. We can also have longitudinal muscles contracting, and they're going to contract in this direction. And so this would be the longitudinal muscles. So these are both in the muscularis externi. And what this is going to do is this is going to cause this area to become fat. And so what's going to look like is kind of like this. Okay. And so the coordinated contraction and relaxation of these two different layers of muscle is what is going to allow for you to move the food down via peristalsis. So coordinated contraction, relaxation is what causes peristalsis. Okay. Now, when the stomach goes down through the mediastinum, where the heart sits, if it goes down behind the heart, it's going to eventually have to come through the diaphragm. So there is a sphincter there. So we call that the gastroesophageal sphincter. It also has another name, which is called the cardiac sphincter. And the reason why is that this is the sphincter that prevents acid from your stomach from getting up into your esophagus and giving you heartburn. Okay. So the sphincter is just a valve that prevents backflow. So this is the valve that prevents backflow. So we have different sphincters in different areas. Technically, our mouth is a sphincter and our anus is a sphincter. But we have the gastroesophageal, we also have the pyloric, and then we have the ileocecal valve between the small intestine and the large intestine. So this is actually formed from the esophagus going through the diaphragm. So it is due to, anatomically, due to the esophagus traveling through the diaphragm.
That makes the valve.
Yeah. So it's not a very good valve is the problem, which is why we get heartburn. Right? But it also allows us to vomit. And vomiting is good if it has a reason. So like if you've ingested something that's toxic and you don't want it to get into your small intestine, you want to vomit it back up, right? So because it's not a very good valve, it allows sometimes things to move in the wrong direction. Okay, so sometimes this valve does not work very well, and then we get parts of the stomach protruding above the diaphragm, and this is called a hernia, and specifically it's called the hiatal hernia. So herniation is where tissue has protruded through something. This case, it's not the outer body wall, like when you think of herniations, like in your abdominal region, but this means that the stomach protrudes above the diaphragm. And this is very common, and it tends to happen in females when they're pregnant because of the pressure of the developing baby. So sometimes their stomach gets pushed up too high, right? And it causes heartburn. So this causes lots of acid in the esophagus. And this acid in the esophagus is particularly bad because it can lead to esophageal cancer. So if you have chronic heartburn, they're really concerned. If you have heartburn for like years and years and years, they're concerned that the esophagus is going to become so damaged that the cells are going to mutate, and then you're going to get cancer of the esophagus. And then some people have to actually have parts of their esophagus removed because of the cancer found in it. And so one thing that they're able to do is they do a procedure where they pull the stomach back down, and they use muscles that are already nearby to kind of wrap it around and keep the stomach below the diaphragm. So if we look at a picture of this, it looks like this. So this is a picture where we have the stomach, and this is gastric tissue. So this is the part of the stomach that has protruded above the diaphragm. And notice that there's nothing from keeping the acid that's produced here from getting up into the esophagus. So if we look at naturally, this image does not show the esophagus, but, or not, excuse me, the diaphragm, but the diaphragm would kind of sit right like that. Okay. So the gastroesophageal sphincter is closed there, right? And then it opens up as we get food pushed down into it. Okay. So we'll talk about the stomach, and then I'm going to show you a short little video that is kind of fun that talks about the hormonal regulation of stomach secretions. So the stomach is important primarily because it is used to store food. So it is used in storage of food and liquid. So we'll put water. So supposedly your stomach, the average stomach, can expand to up like 2 liters. So if you think like a 2-liter Coke bottle, right? That's how much your stomach can expand. But when it doesn't eat, when you don't eat a lot, then it kind of shrinks back down, right? So people talk about, well, I haven't been eating a lot. My stomach, I can't eat as much anymore because my stomach's shrunken. And that's true, that it kind of will decrease in size if you don't eat large meals. So when we look at the storage capacity, this is important because this allows us to eat large meals, which means that we don't have to eat all the time, right? So you could, technically, you probably get away with 1 large meal a day to get all of your nutrients. Most people have 3 large meals a day, right? If you didn't have this, imagine that you would have to eat small little meals continuously throughout the day because you wouldn't have any place to store the food prior to it being broken down and digested. Okay. So it has folds, and these folds are called rugae. So by expanding, you get rid of those folds, and the stomach can expand or it can contract back down. Okay. We actually have 3 layers of smooth muscle. So this is the only organ in the digestive tract that not only has circular and longitudinal, but it also has oblique. So it has plus oblique. So those go to the side, oblique, like this, right? Smooth muscle layer. And this gives us some information about the other thing it does, which is mechanical digestion. So the churning of the food, churning of food is mechanical digestion. So the stomach is a big muscle. Now, sometimes when you think about food and your stomach is empty, it will start churning, and when it churns and there's nothing in it, it makes those growling noises, right? So you might just think about food and your stomach will start to churn, right? And that's getting ready for mechanical digestion. It also has mucus, and so the mucus membrane is really important because this protects the stomach from self-digestion. So if we think about the lining of the stomach and how it differs from the esophagus, there's not a lot of friction in the stomach because the food is not kind of, being forced down through it. And so the lining is simple columnar epithelial tissue. So it's a single layer of column-shaped cells. And then there are cells that are kind of in there that might look something like this. And these are called goblet cells. And the goblet cells are what produce the mucus. So this is my goblet cell. And it produces mucus or mucin. And when mucin, which is a protein, mixes with water, that's what produces the mucus. Okay, so the mucous membrane is super important. So there are some things that can break down the mucous membrane, one of them being alcohol. So when they talk about alcohol causing your stomach to bleed, the reason why, if you drink alcohol on an empty stomach, it will go through the mucous membrane and start to be absorbed across the surface, but it'll damage the lining and your stomach will bleed because of that. So you'll get gastric ulcers. Okay? So gastric ulcers are bleeding due to damage of the mucous membrane. Okay, so alcohol, salt, aspirin. So like the worst thing you can do for your stomach is like after a long day at work or school, going home and having potato chips, a beer, and then taking some aspirin, right? Because your stomach is gonna bleed because of that. It's a bad thing, okay? So you should always eat. So if you're gonna drink alcohol or eat salty stuff, you wanna eat first, right? So that your stomach has some buffer in it, so the food will help buffer the alcohol and the other chemicals that could cause damage to the mucous membrane. Okay, so when we look at the lining of the stomach, there is chemical digestion that occurs in the stomach. So in the epithelial layer, we have what are called gastric glands. And they're actually in little pits. They're called gastric pits. And I'm going to show you a video next Wednesday, or this Wednesday actually, that shows a picture of the gastric pits producing the gastric fluid. Okay? So in the gastric glands, we have two different types of cells. We have what are called sheath cells, I spelled that wrong, sheath cells. And these produce pepsinogen. And then we have parietal cells. that produce hydrochloric acid. Now, in terms of digestion and enzymes, when you see inogen, that means it's inactive. So we've seen inogen in terms of like the enzyme that causes blood vessels to contract, which is angiotensinogen, right? It gets converted to angiotensin and then it's active. So pepsinogen is in its active form, but it gets converted to pepsin in its active form. So this is inactive. So at first it's secreted inactive, and then it gets converted in the presence of hydrochloric acid to pepsin. So pepsin is the active enzyme. And what type of molecule do you think pepsin breaks down? If you look at the word protein, because proteins are composed of amino acids that have peptide bonds between them. So this breaks down protein. Pepsin. So gastric and chemical digestion is important if we're eating, say, for example, animal meat. So if you think about eating a steak, if I'm going to take a steak into my body, I'm going to chew it up, and then it's going to go to my stomach, and the hydrochloric acid is going to start to denature the proteins in the connective tissue. So the connective tissue in the meat will start to break down. And then pepsin specifically will help to digest the proteins in the animal meat. So if I'm more of a vegetarian, then I'm probably not going to produce as much pepsin or hydrochloric acid because that's not needed to break down most vegetarian meals. And so if you are vegetarian, like I'm mainly vegetarian, but if I go to somebody's house and they're like feeding me really good steak, I'll eat it. But it's really hard for me to digest it. Like I can feel it sit in my stomach for a long time before it actually moves out of my stomach and then into the small intestine, right? So protein digestion is what takes place in the stomach. So if we look at an image here, this is my diagram of my stomach. Notice the rugae, notice the folds. The lining of the stomach is the mucosa, produces the mucous membrane, and it protects it from the hydrochloric acid and the pepsin. There's 3 layers, longitudinal, circular, and oblique, and so that allows for the churning of the stomach. When we look at the gastric glands, so if we look at the epithelial tissue, notice that it's a single layer of columnar epithelial tissue. And then if we get down into these glands, then we have the chief cells and the parietal cells. So here's the chief cell and the parietal cells. Right? So the chief cells producing pepsin, the parietal cells pumping out hydrochloric acid. The other cells that are important in here are what are called the enteroendocrine glands. So also in the gastric glands, we have enteroendocrine cells. And what kinds of things do you think they produce, if you look at the word? What do endocrine glands produce? Hormones. Okay, so these produce hormones. And specifically, serotonin is an important hormone for the digestive system. We talked briefly about this when we were talking about the enteric nervous system and how 90% of our serotonin is actually stored in our digestive system, and this also affects mood. Okay? And histamine. Histamine is actually also a hormone. So these are 2 examples of hormones. And then we have gastrin. So gastrin is also a hormone. So those 3 substances are produced by the enteroendocrine. Okay? And they cause, and they help to regulate digestion, right? So help to regulate. By controlling secretion. So yes, there is some nervous regulation, and I'll show you in the video, it talks about nervous regulation, but there's also hormonal regulation of digestion. So this is a fun video that talks about an experiment that was done that allowed us to first identify what was going on in the stomach. And so this is the story of the guy that got gut shot, and then it never healed up, and then the doctor got to do little experiments on this person.
Canadian fur trapper named Alexis St. Martin was going about his business near Lake Michigan when he was shot by a hunter, right in the stomach. The wound was severe, and everyone expected St. Martin to die that night, but he didn't. A local army doctor named William Beaumont kept him alive. In fact, Beaumont performed so many surgeries on the injury over the next several months that he decided, somewhat questionably, to just keep St. Martin's stomach wound open. St. Martin was left with a hole, or fistula, in his abdominal wall, which allowed anyone to see right into his stomach. Now, it's probably hard to work as a fur trapper with a hole in your guts, but Beaumont saw, or possibly created, an opportunity. He hired St. Martin, technically as a handyman, but really as a guinea pig. Over the next several years, in some 238 experiments, Beaumont recorded what St. Martin ate and what his stomach did to his meals. Sometimes they just skipped the eating part altogether and just shoved some food tied to a string right into the guy's gut hole. Beaumont took samples of gastric juices and had them analyzed by chemists, something no one had ever done before. And he also noticed that St. Martin's digestion slowed at certain times, like when he was sick or stressed. I mean, like beyond the stress of having a gaping hole in your abdomen. Through his somewhat questionable research, Beaumont discovered some major secrets of the digestive system, like that the stomach's extremely strong acids and muscular contractions break down food, and that some foods are more digestible or less digestible than others, and that the brain can affect the stomach. Beaumont's findings, as well as his methods of clinical observation, revolutionized the field of physiology. And St. Martin, don't worry about him, he lived to be 83 years old, had great health and a hole in his guts. Now, I sincerely hope that you can't actually see what's going on in your stomach, but let me tell you, the story there is epic. In your digestive system's mission to disassemble food into its tiniest, most basic molecular forms, the stretch that runs from your mouth to your stomach unleashes all of the mechanical and chemical powers at its disposal. It physically roughs up food, douses it in protein-loving, acid-triggered enzymes, reduces it all into a creamy paste, and as a bonus, because it likes you, it also kills a whole host of harmful invaders that, for whatever reason, found their way through your face and into your tube. But your stomach's not the end of the line for your food, unless it is. I mean, most of the time, everything from your mouth to your stomach prepares food to be absorbed by your tissues, but sometimes food finds its way back up. Yeah, in case the story of Alexis St. Martin didn't make you want to do this already, now I'm talking directly about vomiting. Let's begin with the beginning, with your mouth, aka your oral or buccal cavity. Now, we don't usually think of it this way, but that is where digestion starts, the mechanical and chemical breakdown of food through chewing and enzyme action. The inside of your mouth is lined with a tough, thick layer of stratified squamous epithelium that can stand up to lots of friction, like getting scraped by tortilla chips and like grilled cheese sandwiches that maybe were cooked a little too much on the top. Your anterior hard palate and the flexible posterior soft palate form the roof of your mouth. The hard palate provides like a hard surface for the tongue to mash food against, while the soft palate forms a movable fold of flesh that reflexively closes off the nasal pharynx when you swallow, so food gets directed down your esophagus and not up into your nasal cavity. We all know what teeth are for, and you have roughly 32 of them in your basic types that help you masticate or chew your food. The tongue lives on the floor of your mouth and is basically just a big muscle that grips and constantly repositions your food as you chew. The resulting ball of mush actually has its own special name. It's a bolus, and the tongue rolls it back to the pharynx in preparation for swallowing. But that's just the physical action that goes on in your mouth. Just as much destruction is taking place through chemistry. The bolus is broken down with the help of three major pairs of salivary glands that churn out an average of 1.5 liters of slightly acidic saliva every day. More than 4 soda cans worth of spit. per day. And all that saliva delivers enzymes like salivary amylase, a digestive enzyme that breaks down starches into glucose monomers. Now, once the food enters the pharynx, it's propelled by peristalsis into the esophagus, which, except for the little sphincter at the end that keeps food moving in the right direction, is really just a glorified laundry chute lined with smooth muscle. The only time you probably even remember that you have an esophagus is when something's stuck in there, or if you're feeling intense heartburn, or you just puked. But moving on, assuming you had not just puked, then the bolus moves on to Dr. Beaumont's ticket to fame, the stomach. The stomach is the stretchiest part of your digestive tube, capable of holding 2 to 4 liters of material at any given time. 2 to 4 liters. That is a lot of nachos mixed with steak. But of course, it's much more than just a storage tank. It's lined with the same 4 main layers found for most of the GI tract: the mucosa, submucosa, muscularis externa, and serosa, but it's got a few special modifications. For one thing, the muscularis includes an additional layer of smooth muscle that gives it extra strength, allowing the stomach not just to hold materials, but to actively smush them around. And the inner mucosa is made up almost entirely of mucus cells, which produce a protective coat that keeps the stomach tissues from getting digested along with your lunch. This inner lining is dotted with millions of tiny, deep gastric pits, which lead down to tubular gastric glands. These glands, in turn, contain various types of secretory cells that brew up some of the most potent chemicals in your body. For example, your stomach has parietal cells that release hydrochloric acid, a substance more acidic than battery acid, which lays waste to most of the bacteria, viruses, and other stuff that could make you sick. It also helps denature or change the shape of proteins to make it easier for enzymes to digest them. And maybe more importantly, when the hydrochloric acid is combined with pepsinogen, an inactive enzyme that's secreted by another kind of stomach cell called chief cells, the mixture creates the protein-digesting enzyme pepsin. Together, this superpowered acid and protein-hungry enzyme can annihilate nearly anything they encounter. This was apparently something that Beaumont observed firsthand by dropping chunks of meat into a cup filled with St. Martin's personal gastric fluids. He watched the gobbets of food dissolve over time, which is partly how he discovered the stomach's role in digestion was as much chemical as mechanical. But with so much mind-blowingly powerful stuff at your stomach's disposal, somebody down there has to be in charge. So your gastric glands also contain enteroendocrine cells. These cells release regulatory hormones like serotonin and histamine, which act locally to trigger other cells that, say, release more acid or contract muscle tissue. And when the time comes to tamp the action down, they secrete other hormones like somatostatin to inhibit secretions. And then there are G cells, which produce the most important hormone for stimulating gastric activity, gastrin. Most signals that increase stomach activity get the job done by increasing the
I'm going to pause this because we're going to talk about this a little bit more, and we're out of time. So here's your crash course review summary. If you haven't discovered that, that's on Khan Academy. So they have all kinds of review. If you want to review the immune system, the respiratory system, the lymphatic system.